How you guys doing today? Good, all right? So it's Friday, so we're about to have a weekend. Right? So I don't know if you guys watched the video on YouTube. I actually finished all chapters, I think Wednesday. So from today, we're gonna do lots of review. Okay, so you'll be really fully ready for the final exam when we have the final exam on the Canvas online. So there will be final exam will be online on Canvas as you guys did for the quizzes. That's where you're gonna do the final exam too. So it'll be actually open book test. So you don't have to memorize anything. You only need to know how to solve the problem. Then it's all in your book and the PPT. All right. So the first one I can try is can you guys write the electron configuration form? Or nitrogen. Okay, let's try the nitrogen. Okay. So you need to look at the periodic table, right? Okay. And see where the nitrogen is. There. Okay. So you can try it too, like condensed one or just a long version, either one. Okay, so yeah, here's the thing. If you look at this one over here, this first period is the S block. Okay, this is 1, 2, 3, and so on. And this first two column is also S block here. This is P block. You're gonna have a P block here and the F block over there. So you just need to read the left to the right, top to bottom. Okay, so be 1. This is S block, right? So 1 S 1 2. Okay, 1 S 2. So you got to the lower period, which is 2S. So it'll be 2S 1 2. Okay, so it'll be 2S 1 2. And this is also 2, but in P blocks it'll be 2P 1 2 3. There you go. Okay, so you can do the electric configuration form for elements by just following those ones, and just remember what the orbital box is in each column and everything. Okay, S P D F. Okay. And then if you want to do the condensed version, you can just go, right above the one upper period and the noble gas one. Then we'll switch to this one. Okay, so the helium in bracket. Then you can just start with where you have the elements you're looking for in the same period. So it's 2s2. So it'll be shorter. Okay, condensed one. Okay, makes sense, right? Okay, let's do just one more and move on. Can you guys try the sulfur? Okay. Let's try chlorine. Here. Okay, about 1 minute, right? Just do the long version and shorter one. Okay, so yeah, if you look at this one here, same 1s 1 2, so it'll be 1s 1 2, 2s 1 2, okay, and 2p 1 2 3 4 5 6, 2p 6, and now the 3. This is third row, right? So the 3s 1 2. and then it will be 3, 2, right? So it'll be 3p block, this p block, so 3p, 1, 2, 3, 4, 5. So just like 5. Okay, that's the electric configuration from forward chlorine. If you also do the condensed one with using the neon here, because the right offer period noble gas 1 neon. And then you can start from the way you're chlorine in the period, so it'll be 3 S2, 3p, 5. This is also the same thing. Okay. So the makes sense, right? I mean, you just need to follow the. Okay, let's try to do this one. Okay, it's about 30 seconds. We'll do this too. We just add one more electron here. Okay. All right, so I'm gonna add one more electron here, which is what? 6, right? 6. Okay. So you can have a long configuration here. You can make it shorter, right? It will be just exactly the same as what? Electric configuration form of argon. It's just the same. Okay. So once again, they're still not the same because they still don't have the same number of proton, but they only electric configuration wise same. So we call this iso electronical the same. So numbers of electrons are the same, but they're still not the same element because different numbers of protons. Okay. But obviously, if they become electric configuration of an noble gas, it will be more stable for sure. Make sense, right? Okay. All right. This one. Okay, this is kind of a long trip. I mean. Do you guys still remember the quantum numbers? Quantum numbers, okay. So here's the thing. You have N, L, ML, okay, and MS. Okay. So those the first 3 is for your orbital, what orbital you have over there. Okay. And this is about your electrons in a certain orbital there. Okay. So. Here's one thing you can do is the n. The lowest possible number for n is 1. So n cannot be 0, okay? Because the n stands for what? Principal quantum number. So it calls principal because the n start the everything, those 3. So n number will govern those 2. I'll tell you why. Okay. So this has to be at minimum 1. And as you know, it can be 1.5 or 1.7 because now we believe in quantized energy, so it'll be 2, 3, and 4, nothing between, okay? And then for L, it can start with a 0. That's okay, because you may not have a angular momentum on your orbital, which is a spherical. So this, if that is 0, is S orbital. 1 is the P orbital. 2 is D. 3 is F. Okay. This is a kind of a outside of the class, but have you ever thought about even bigger orbital than F? Because I'll stop here. Okay, so this is the term here. So here's one thing I want to tell you is that L, okay, L max means maximum number you can have for L is the n minus 1. Okay, so if you have like a n equal to 3, the maximum number you can have for L is 2. Okay? Means what? You can also have maybe 1 or 0 as well. Okay? But you cannot have F orbital if n is 3, because the max number for L should be n minus 1. Okay? So this is another thing. And then whenever you have an L number, ML should be this one. So if L is maybe 2, okay, then possible ML you can have is -2 to the 2, and including all the integers including 0. So it would be -1, 0, and 1, and 2. So it would be 5. That is why your D block has 5 orbital bucks. Okay? So you have an ML. So possible ML from the L is equal to 2, with -2, 1, -1, 0, 1, 2. Okay? So this is like a negative L to L combination, including 0. That's the possible ML you can have for magnetic quantum number. Okay. So here's just one thing for MS. Magnetic spin for electron is always either up spin or down spin. So you only have 2 choices, either plus 1 of 2 or negative 1 of 2. Okay? If it's up spin plus, if it's down spin, it's negative half. So I'm not going to explain why there was only 2, but that is the magnetic spin for the electron. Okay. So does it make sense so far? We good? Okay. So if I give you the quantum number combination, so I will show you the quantum number. Combination. There will be 4 quantum numbers, right, in total. So if I say n is 3, okay, and I can say L is 1, and L is the -2, and this one is negative this one, okay. So if you look at this one over here, do you see anything wrong in this one by following what we just did over here? So n is just 3, right? So that means L can be either 2, 1, or 0. Okay, but there is 1, so that's okay, right? But ML, the L is 1, right? L is 1, so ML choice can be -1 to 1, including 0. But you have a -2, right? So that means this quantum number combination is false. It doesn't work because it's outside of your possible combination. Does it make sense? So same here. If you have this quantum number combination, so this is maybe 2 and 2, -1 and plus this combination over here. So they all look fine because this is L is 2. Then you can have a -2, -1, 0, and 1, and 2 for this one. It's just -1 is right here. This is okay too. And you have a up spin over here, the electron, it looks fine, but n is only 2. So you actually could not have 2 for L, but the max number you can have is only 1. So that's also wrong. Okay. So if that makes sense, you can have I'll give you 4 combinations, and you can say which one is wrong. Okay. Maybe you can say 2. Try this. See where if you did something wrong, you can fix. You can find out where that is. Okay, about 1 or 2 minutes. this sometime. Okay, so this looks fine, right? Okay, this looks fine. How about this one? This is something wrong with this one, right? Because the maximum number for L you can have from N3 is 2. So it has to be actually 2 as an X. Okay, so this is maybe wrong. How about this one? This has 2, 1. Okay, looks fine. And then so if it's 1, -1 to 0 and 1. So this also looks fine too, right? And this one also looks fine. So it looks good, okay? How about this one? You have 3, okay? So maximum you can have 2 or 1 and 0. So 1 is there, it's good. And also 1, -1, 0, +1. So MA also looks fine because it's one of your choice. But your magnetic spin is +1, which I think it doesn't make any sense. Because yeah. So then this is also wrong. Makes sense, right?
How do you know when to put plus or minus one?
Oh, the last one, right? So that is only for it only indicating the electron. So the if you have some p blocks, s block, and d orbital, sometimes you can fit the 2 electrons in each box in orbital diagram. But you just indicating if it's heading up or down. So your electron always spinning, meaning, so if you have some thing that has electrical charge, if it's either plus or negative, if it's moving, it generates the magnetic field, meaning they're going to have some magnetic force. So either they're going to rotating either side, either they're going to show some electric field direction either up and down. So we just doing for +1/2 and -1/2.
Is
So
there any way I can tell by the numbers given or no?
for electron, yes, you can, but I'm not gonna do that on the exam because I don't want you to do the counting the electron in each orbital and locating. I can do it, yes. For example. Nitrogen. So you have a nitrogen over there, right? So there will be 1s2, 2s2, and this will be 2p3. Okay? So then you're always going to use the most outer shell. So this is 1s is a field, 1 and down. 2s is also 1 and 2, but p has a 3 because it's -1, 0, and +1. So the 2p has the 3 boxes there. But it only 3. So the way you need to fill is following the Pauli exclusion rule. You have to do up spin first. Do you guys actually remember this one? You fill the electron up first. You guys remember this one? Okay. So if you're looking for the quantum number configuration for this one, this will be the plus the 1/2. If it was the oxygen, your last electron of the quantum number for the last one would be -1/2. But like I promised before, I would do that on the exam. So yeah, so as long as you can do this one, you'll be just fine. All right, let's move on to the next one. Okay, so if you have iron, okay, so just arrange them in order of increasing the atomic size. Okay, so arrange them in an order of increasing the atomic size. Okay. Okay, about 10 seconds. So yeah, what might be the smallest one? Can you guys guess? Perfect. Nice, nice. Okay. So just remember, if that elements become a cation, it will be smaller. So that's why if it's 3 plus, it will be smallest. 2 plus, somewhat smaller than element, but this will be the biggest. Because think about it. You have a atomic structure. It's simply what? Nucleus at the center. You have an electron density, or you can say numbers of electrons with a certain distance from the nucleus there. But if you have a less numbers of electrons around the more numbers of proton, this central attractive force will be stronger to the center. So meaning your overall size of the atom will be what? Decrease. That's why you have a more positive charge will become smaller in size. Okay? So it will be actually what? Vice versa on what? Anion, right? So as you can see, if you have this one, maybe you can do this one. So if it becomes anion form, bigger, cation, smaller, element form, it just stay the same. Okay, so far so good. Okay, all right. So just you can do this, right? Okay, looks good, right? So this is the element form. Cation will be smaller. The anion form will be bigger than OH. Okay, looks good. All right. So let's move on to. Okay, so. Ionization energy of sulfur is greater than ionization energy of oxygen. Okay? True or false? So look at the periodic table. Okay? So you need to remember the general trend of ionization energy, which will be totally opposite to one of the atomic size trend. Okay? So look at the oxygen and sulfur there, and see if that statement will be true or false. Okay. Okay, what do you guys think? Will be true or false? Okay, oh, false. Okay, good, good. So here's the thing. You're confused because you just thought about the genetic trend of the size. So obviously, the size of the sulfur will be bigger than oxygen, because when you look at the periodic table, when you go from the top to bottom, the atomic size will increase. Okay, because you have more numbers and quantized energy where you can store the electron. The size of the atomic atom will be increased. So size-wise, yes, sulfur is bigger. Actually, that means this one will have a lower ionization energy than oxygen. Because think about it. Whenever you have atoms are having some electrons here, okay? So we call them inner electrons because it's in the inner shell, and the one on the most outer shell is the one that we actually call valence electron. Do you guys remember this? Valence electron, which can be used for making covalent bond. Do you guys remember this? Okay. So if it's bigger in size, it actually be lower in ionization energy because it's easier for them to lose electron far away from the nucleus. Because the interaction here and here will be very weak, right? Then if it's bigger in size, it's easier for them to lose electron, meaning they become easily ionized. So ionization energy of the sulfur will be actually lower than oxygen because it's bigger in size than oxygen. Makes sense, right? So it's literally opposite to each other. So general trend of atomic size, general trend of ionization energy will be opposite. Okay? So yeah. Okay. Okay, then. All right. So how about this one? You have a sodium is bigger than magnesium in size. What do you guys think? True or false? Look at the periodic table and see what you can do. So this is the size, and says the sodium should be smaller. What did I say? So sorry. Sodium is larger than magnesium. Okay. Is it true or false? So look at the sodium and magnesium. They're on the same period, right? So just remember one thing. If those elements are on the same period, same row, if you go from the left to the right, the size will decrease. Okay? So technically, the sodium will be bigger than magnesium. So this is actually true because of the general trend. Do you guys remember why it's smaller across the period? You don't have to know, but this is the general trend. It's just because of the quantized energy. So as you go over more numbers of electrons, it's not gradually increasing the size. It only stores the electron in certain orbits, some orbitals. So there's a limitation of the expanding the size of the atom by putting more numbers of electrons. But if it's in the same row, meaning they only can use the same numbers of what? The orbital. So then more numbers of proton will pull the electron to the center strongly. That's one. Anyway, okay, so this, here's the thing. Metals tend to form cation. Anion. Okay. True or false? So metals wants to be anions. True or false? Okay, so this will be, what do you guys think? So metals actually tend to be cation. So that's actually wrong. Okay. Okay. Let's see. All right. So you have a alkali metal. And then alkaline earth metal. Okay. The reactivity to water. And how about this one? True or false? So it says alkaline earth metal is more reactive to water than one's alkali metal. Is it true or false? So the alkali metal is a group 1 element, which is mainly metal except hydrogen. This is alkaline earth metal is group 2. They are mainly also metal as well. Yeah. Okay, so this is actually fourth. Okay, because the alkali metal is much more reactive to water. So it actually kind of makes sense. You don't actually have to memorize this one because you know how to do the electric configuration form for first column and second column, right? So think about it. For example, if you have sodium, okay? Sodium is what? The 3s1. Sodium is 3s1 with the neon. Okay. And then the magnesium, which is alkaline earth metal, is the neon 3s2. Okay. So if you look at the diagram right here, this is the s orbital diagram, which is only one box, because that is the L is a 0. There's only one ml, which is a 0 as well. So you can do only 1 electron field in that orbital, which you can actually feel 2 electrons at max. But if this one here, your magnetic field only heading up, there's no electron make it even. That means this will become what? Unstable, because you have only upspin electron in the 2 open spot, the orbital box. Okay. This one has the 1s orbital box, same, right? It's 3s orbital box, but it has 2 because it's group 2. 1 up, 1 down. So it looks just fine as it is. It's very quite stable, electric configuration wise. So if this is unstable, so unstable means what? They want to react with something to be stabilized. So when they react with water, they want to drop the electron almost right away. So that is why ionization energy for the group 1 is very low. They just want to drop the electron just so quick, meaning they're very reactive because they want to do reaction with water. So reactivity of the water, of the alkali metal is very high. Okay, but this one already quite stable, not so much. But once they do first ionization, they become really unstable, and then they do the reaction. So this is only somewhat reactive to water when you get down to the column, but alkali metal, yes. Except the hydrogen, they explode with water. Makes sense, right? Okay, how about this one? So the statement says the ionization energy of noble gases in the group 8 have very low ionization energy. How about this one? True or false? So the noble gases means the last column, the group 8, the last column in your periodic table. Helium, neon, argon, chromium, xenon, and radium. Okay? All right. So what do you guys think? True or false? False, perfect, great. Okay. So as you can see, this is the one that has the smallest in the same period, meaning opposite to the trend of the size will be very high. And also, think about it. The noble gas is called noble gas because they don't do any reaction, because they're very stabilized. So if you have something to make it react with something, you have to have lots of energy to do so, because they don't want to react with anything because they're already stable. So if you want to make that noble gases interact with something else, you have to put lots of energy, like heat energy or pressure, a lot of light energy, maybe something. So then they may work, but it only may work when you get down to the near xenon. Even though this is also outside of the class, even though it's noble gas, they're not always stable, especially when they got to the very heavy noble gas. Because of this size, it's so much energy keeping the noble gas warm. They sometimes become reactive. So xenon sometimes react with the halogens, but upper like neons and argon is readily very stable. Those are the gas we use for chemical reactions, because you can have all the conditions very stable, except the one you want to do the chemical reaction with it. So we're not affected by other elements. Okay, makes sense, right? Yeah, I mean that's not. Yeah. All right. So okay, you can say silicon is one of metalloid. True or false? So metalloid simply means you're gonna find most of the metal on the left side of the periodic table, most of the non-metal on the right side of the periodic table, and somewhere between you're gonna have some elements that has somewhat metal and somewhat non-metal. So they're kind of like half and half in both. So I give you the Silicon Valley as one example of the metalloid. So this is actually true. Okay, so you have So metalloid trends over there, that based on okay, so I'm not gonna talk about the why metalloids has half and a half. I already told you last time, but yeah, you don't have time for this. So I think that's it for the covering chapter 7. So probably we have some 5 minutes. I'll just cover a little more of the other chapters and we'll finish. So let's do this one. Okay? So you can have so you have 4 numbers there, and I just want you to find out how many suffixes are there for each number. So 1, 2, 3, 4, and just go ahead and find out how many suffixes are there for this number. Okay, so this one, what do you guys think? How many? It's 5. Let's count them all. Because your 0-digit number is between non-zero, so you count as a suffix as well. Okay. And this one is also 5. So if you have some numbers that is bigger than or equal or bigger than 1, and with the decimal point, you count all the digit number as a suffix. So no matter what, if it's bigger than 1, decimal point right there, count them all. Okay, that's it. How about if it's less than 1? If it's less than 1, you count the first non-zero digit number after decimal point and count after. So that would be 4. 4. Okay, and this one is pretty much the same. You count the first non-zero number after decimal point is right here, and this 0 also in the non-zero digit number, so it'll be 3 suffix right there. So there are several rules. You can just keep that in your mind. It'll be just fine with any kind. So actually, there was one tricky example I gave you. I don't think I'll put this on the exam, but this one was a tricky one. Okay, so if you have a 1,000, but there's no decimal point, then it's bigger than 1. But the problem is you have a non-zero digit number on here, but they're all 0 numbers after. Okay, so in this case, normally we assume only 1 suffix are there. Normally we do, but maybe there are 2 or 3, maybe 4. We don't know for sure, but for sure there will be only 1 suffix. At least is the one thing we can be 100% sure. So that is the reason why we had to use sometimes what? Scientific notation. So if I put this, it's 1,000 here, right? But I put 1.0 times 10 to third, okay? Then this is also 1,000 too, right? This is also 1,000, this is 1,000. But I do know for sure, and here, it has only 2 suffixes on there. So instead of putting 1,000 like this, if I put this in the scientific notation, the readers will find that, oh, there is only 2 suffixes for this number for sure, because there's only 2 there. So if I put this one, still the same number, but with this 3 suffix. Okay, so this is kind of arbitrary. This is very clear. Makes sense, right? Okay. Yeah, I will not do this anyway, but yeah, just for you. So I will stop here today. Let's do extra credit.